quality. Thomas, floor is yours.
Okay, thank you, Robert. Let's chip it away with a brief introduction to the world of sound imaging and what you can currently find in the market. So acoustic cameras today essentially come in different variants, but essentially they are based on one specific technology, which is massive parallel audio data acquisition of typically more than 100 microphone signals. And what all of these systems have in common, or what essentially makes a good acoustic camera, is a large measurement surface, and along with that, a high number of distributed microphones. Especially in product design and testing of industrial products, low frequency sound emissions are common, and those can only be perfectly localized if the measurement surface or the diameter of the measurement surface is large enough. At the same time, also the number of distributed microphones across that measurement surface plays a crucial role in order to understand what the dominant sources and what the secondary sources are. All of these systems that you may currently find in the market today are based on beamforming, which is a special type of signal processing based on processing hundreds of microphone signals and determine where in space a specific sound event is coming from. Having said that, with current system, there are also a couple of limitations, especially when it comes to the high performance systems. As we said before, best spatial resolution and dynamic range is only assured if there is a large enough measurement surface and a high enough microphone count available. But that also means that the associated equipment is heavy. So we're easily talking about 20 kilograms plus. The equipment is also bulky. A long setup time is involved, typically in the order of 15 plus minutes to really get started with acquiring the data and with analyzing acoustic images. And we are also easily talking about a price tag of 40,000 euros plus in order to get to the best image quality performance in the field today based on traditional acoustic camera technology. What you may also find in the market today is the handheld systems. So these systems have entered the market some 5 to 6 years ago, but they are mostly only used for special applications. So when it comes to localizing leaks in compressed air systems or partial discharge in high voltage insulators, these are typically high frequency sound events, even outside of the audible frequency range. And this is why a large measurement surface is necessarily not required. And this is why these systems are typically built up in a very compact way, but again, limited to the number of applications that can be served. So now, and we have tried to address this issue of assuring or ensuring high image quality or best image quality while offering a compact, lightweight system and also cost-attractive system at the same time. And the technology breakthrough that we have achieved is coming through the so-called sound field scanning technology. So we only use a handful of microphones which are distributed across a rotating stick. And that stick is rotating at moderate speeds in the order of 1 to 3 revolutions per second. And by doing so, we can actually acquire the sound field at 400 plus virtual microphone positions. And that brings me back to the two main advantages of, or two criteria, which eventually make up a good performing acoustic camera. It's size of the measurement surface. Having such a technology, you can arbitrarily scale the system to very large measurement surfaces. And at the same time, we acquire the sound field at a huge number of microphone positions, thus ensuring high image quality. At the same time, since we do not acquire that much data from that many microphones, we can enable cloud processing, meaning we can send data to the cloud and have the data processed there, sent back to a dedicated mobile device for further analysis in the time and frequency domain. At the same time, as said before, the system is lightweight and it's low cost by design. On top of that, you essentially get a system that covers a very wide range of applications. As you will see later on, we offer up to 4 different sensors, rotating sticks, so to say, which can cover low frequency applications up to high frequency or even ultrasound applications. The usability is unique in the sense that we leverage mobile app technology. So it's not an overloaded user interface with a ton of buttons, but it's essentially what you know from operating your mobile device on a daily basis, a quite intuitive mobile app user interface. The setup time is in the order of 2 to 3 minutes out of the box to the first image or to the first result. And the equipment is also suitable for deploying it in the field and also in harsh environments. Here's a brief overview of our SoundScanner sensor portfolio, starting from the far right, the P254, which is currently the largest mobile acoustic camera in the market, having a diameter of roughly 2.5 meters. And the starting frequency is 125 hertz. Mostly used for localizing sound emissions from products like compressors, electric drives, generators. The P132 has a diameter of 1.3 meters. Starting frequency is from 250 hertz upwards. It's very popular with companies and users active in the industry, in the HVAC industry, vendors and manufacturers of CNC machinery, power tools, and also powertrain components in the automotive industry. Moving further to the left, we have the P50 having a diameter of 50 centimeters. And as you already may have realized, as we go down to smaller measurement surfaces, smaller diameters, the lower frequency goes up. So the P50 is starting at 700 hertz, mostly used for locating bus squeak and rattle sounds in confined spaces, where you typically don't have enough space in order to set up one of the larger systems. And last but not least, the P12. This device is equipped with ultrasound microphones. It can locate sounds from 2.0 kilohertz up to 44 kilohertz, and it can be used in applications like leakage localization in car cabins, refrigerators, and machine enclosures. The measurement process itself is fairly trivial. As I said before, the system can be set up within 2 to 3 minutes. You start rotating the sensor. The data is wirelessly transferred to a mobile device, then passed on to either the cloud or a dedicated on-premise solution in the form of a high-performance laptop. The acoustic images are then processed there and sent back to the mobile device for further analysis in the time and frequency domain. We also do have a desktop application, meaning that you can transfer your data from the mobile device to your laptop and leverage advanced software features like defining regions of interest in the acoustic image and gathering more information about the frequency content that is coming from a specific spatial direction. On top of that, we also have automated report generators and artificial intelligence features for enhancing the effective use of our technology and getting you to results quickly. At this stage, maybe let's talk a little bit about acoustic cameras as they are used in design and testing and what the associated benefits are. First off, acoustic issues with a product typically occur very late in the product engineering process. A prototype may be mounted onto a test rig and the expected target sound levels are not met. Also, start of production may only be a couple of months away. So at this stage, if modifications of the product's design are necessary, you better know what you're doing, because if a redesign fails, for instance, multiple months are typically wasted. And this is exactly where the acoustic camera now comes in, helping you to reduce trial and error time during troubleshooting and develop technical solutions which are first time right. Because making things first time right essentially saves you a lot of money and resources and helps you stick to your schedule and get a product launched on time. Also, in many situations, things may get nasty when multiple components are integrated and they start to interact. So let us imagine you're a tier 1 supplier, for instance, and your component will be integrated into a final product. Your component may then excite certain connected structures and component. So it's not your component which is causing the noise, but it is other components that they get excited at a certain frequency and emit sounds over a larger surface. So the solution may not necessarily be exchanging that supplied component, but fixing the other component so that it will be better decoupled or does not resonate that well at that given frequency. So acoustic cameras help you again to gain valuable insights at the integration level and develop the right solutions, especially when problems are complex and many components start to interact. Next, regulatory sound measurements are typically taken on a test rig. And the sound that the microphones pick up may also contain sound emissions from the test rig itself. So in order to avoid any unnecessary contributions, which reduce your margin to regulatory limits, the acoustic camera can be used to understand any resonances or sound emissions from the test rig itself and optimize those. And finally, acoustic images help you understand secondary sound emissions also, which may not necessarily influence the loudness of your product too much, but which may be felt annoying by customers and your end users. And in this particular case, an acoustic camera helps you to single out these contributors, and they may be easily fixed and improve the overall perceived quality of your product. So now let's head on to a couple of very interesting examples which are provided to us by our customers. And first off, I would like to start out with an application from the heat pump industry. Here in this case, we're talking about unwanted sound emissions from a heat pump. In this particular case, the product engineers discovered that there was an elevated sound pressure level, which was some 3 dB above the target specification, and it was measured on the outlet side of the heat pump. And the task was to locate the sources that contribute to that elevated sound pressure level and identify the root cause that is responsible for that. In this particular measurement setup, we have a situation where the compressor of the heat pump operates at an excitation frequency of 110 Hertz. And in this case, we use the soundscanner P132. It's positioned at a distance of 1.5 meters from the heat pump's outlet, and a total of 10 seconds of audio data are acquired. In the beginning, before running the acoustic camera measurements, there was an initial hypothesis from the engineers that they believed that it was mostly a structural excitation of the enclosure panels from the compressor vibrations at multiples of 110 Hertz. So let's take a closer look at the result that we achieved with the acoustic camera. First off, the investigation started on the right side of the outlet. One of the enclosure panels was removed, and the dominant sound sources were located. In this particular case, you see that the dominant sound emissions are happening at low frequencies, and they are mostly coming from the compressor. You may already see here in the optical image that some measures have already been implemented in terms of covering the compressor with some damping material. By the way, the three images that you see here are acoustic images that are taken in different frequency bands. In this particular case, the engineers wanted to understand what is the overall broadband sound emission from the product, where are those sound sources dominantly located, and then you can go into the nitty-gritty details. You can select single frequencies, but you can also select third octave bands, or arbitrary frequency bands that you are interested in. In this particular case, the engineers were particularly interested in getting acoustic images at low frequencies, meaning starting from frequencies at around 250 hertz up to 1.7 kilohertz. You already see in the frequency spectrum in the top right corner of the slide that you see the 110 hertz and multiples of those 110 hertz. And then beyond 1.8 kilohertz, you see some broadband sound, other excitations, also tonal excitations up to 6 kilohertz. When we add or when we put the enclosure panel back on and take another acoustic camera measurement, we already see that the total sound pressure level is reduced by 17 dB. So when we go back again, total sound pressure level before was roughly 80 dB before without the panel. Then it was reduced down to 62 dBA. And coming back to one of the initial hypotheses that one of the engineers had, that it was mostly associated maybe with vibrations of the enclosure panel. This is not necessarily something that we can see here. What we see here is essentially a dominant sound source in the bottom right corner of the fan grill. Across the broadband frequency band, when we look at the low frequency portion, we also see that it's mostly coming from the bottom right corner of the fan grill, maybe also a little bit surface vibrations from the enclosure panel. But when we look at the dynamic, so-called dynamic range of the acoustic image, we see that it is 6 dB below. So the panel itself is certainly a secondary source or secondary contributor. And at higher frequency, we may even localize leakages in the enclosure panel, as you see over here with the blue dot here on the right and left side of the enclosure panel. At higher frequency, we also start to see the fan and again that source in the bottom right corner of the grill. We can do the same measurement also from the other side of the heat pump. We get a similar situation that it's not the fan that is emitting most of the sound centrally through the fan grill, but that there is some sound source more on the bottom part of the fan grill. We can then take off the fan grill itself. We move a little bit closer. And interestingly, when we look at the broadband sound emissions again, you see that the sound pressure level starts to increase again a little bit because we take off the cover and we have less masking from the sound sources. And we see that there is a very dominant sound emission here from this bottom tray here. And what was eventually found out is that you see that there is a wire harness going from the cabinet where the compressor sits over to the other area of the cabinet. And what the engineers later found out is that that wire harness is tied to the structure with cable ties. And that wire harness is excited by the compressor, is essentially exciting then the tray and all of that structure, which is then starting to vibrate and emitting dominant sound emissions at low frequencies. So in the next step, the engineers cut through the cable ties. They took off the wire harness, wrapped it into some elastomer or elastic material so that it was at least some way structurally decoupled from the frame and from the tray structure of the heat pump. And the overall sound pressure level was reduced immediately by roughly 3 dB. you immediately see by looking at the acoustic image that now the fan becomes the more dominant source, and that the wire harness connecting the two cabinets on the left and right side becomes a secondary source and can certainly be further improved. So 3 dB was just essentially the improvement by implementing a quick hack, but there is even up to 4 or 5 dB possible by fully decoupling that wire harness from the structure. So again, just to repeat this, the flow of how the acoustic camera was used in that situation. We started out with an initial hypothesis, which came from the engineers. We looked at the specific section of the heat pump. We removed the cover. We looked at the compressor. We evaluated the effectiveness of the enclosure panel. We put the enclosure panel back on. We then found that the dominant source was essentially sitting somewhere else. We also validated that situation by moving the camera to a different position, looking at the heat pump under a different viewing angle, then taking off the fan grill, stepping one or digging one step further, and then essentially identifying the true sound source or the true emitter of that problematic sound event. The root cause was essentially identified. The component was decoupled, was wrapped into an elastomeric structure, and then eventually the acoustic camera was used to validate that the improvement was eventually achieved. So a very quick process. It only took some 10 to 15 minutes to figure out what the problem was. Let's head on to a next example. This time from the construction equipment industry. And in this particular situation, we're talking about balancing sound emissions from a construction equipment. So here we have an excavator, which misses a regulatory noise requirement by 2 dB. So it was 2 dB above the threshold. And the task was to localize the dominant sound emissions under different viewing angles and identify measures to redirect the sound and come up with a balanced distribution of sound pressure levels all around the equipment, because this is what has to be met during regulatory testing, to meet that regulatory limit all around to the equipment. Under certain viewing angles, you may have more margin, and obviously in this particular case, on the right side of the construction equipment, the corresponding sound pressure level was 2 dB above the limit. Again, the excavator operates in a worst case condition. The soundscanner P132 in this case was positioned at a distance of 2.3 meters from the equipment, and some 10 seconds of audio data were recorded. Again, initial hypothesis was that the muffler and the intake sound, so these two components here sitting here on the excavator, were suspected to be responsible for the violation of the expected noise threshold. When we look at the original image, we see a very complex distribution of sound sources. We have here a very dominant sound source here at the exhaust manifold. We have a secondary source, which is sitting some 7 dB below. Here in this particular case, we have a 7 dB dynamic range in the acoustic image. So the secondary source is coming from the muffler. We can even locate the sound at the exit of the muffler, and we can locate the reflections from the operator's cabin, from the window glass of the operator's cabin. As a next step, the engineers put a metal sheet cover at the exhaust manifold. And you see in the second step, the engineers were able to reduce the sound pressure level under that particular viewing angle by 2 dB, from 75.1 down to 73.1. You see that the acoustic image now looks totally different, and that the dominant sound sources have somewhat shifted. We now have the dominant sound source here at around the fuel cap. We still see the muffler, the sound at the exit of the muffler, and also the reflections at the window glass of the operator's cabin are more dominant now. By the way, the source that you see here on the bottom is a reflection on the ground floor. which is essentially coming here from the exhaust manifold. So in acoustic camera, just as is it with the reflections here on the window glass, they also can, of course, appear on other hard reflecting surfaces, like the floor, as we have it here in this case. In a third step, the engineers also tried to cover the full fuel cap. And in this case, that you see again that the sound sources are somewhat shifting again, and that most of the sound is exiting through the opening on the fan side now. So you see, as you try implementing certain things, or as you try to close certain openings in a structure where dominant sound sources are, the sound is somewhat rebalancing itself, or sound emissions are somewhat rebalancing themselves and are being emitted then in other situations. But the most important thing is that you can always quickly iterate and prove that you have made an improvement and try to understand where the sound emissions are now happening in the end. Overall, a 2.1 dB reduction was achieved, which was exactly the goal or the target value that was necessary in order to get below the regulatory threshold. Last but not least, a very brief example from the household appliances industry. Here we are looking at leakages in a refrigerator door. In this particular situation, the task was to locate leakages in the door seals of a refrigerator door prior to submitting that product or test sample to a cooling performance test. So here in this particular case, we use an ultrasound speaker, which is operating at the frequency of 40 kilohertz outside of the audible frequency range. This is also very neat and important because you can run this test also in a very noisy production environment, essentially, for doing quality control. Since you're doing the test way outside of the audible frequency range, where contributors from machinery or people talking or other machinery noise may not be contributing at all. The SoundScanner P12, which is a very compact device in this case, is pointed at the refrigerator door at a distance of 1.4 meters. And the engineers did the measurements on the left section and the right section of the refrigerator, and they identified 3 critical leaks. Those leaks are also quantified in terms of a sound pressure level value. And when you ran a cooling performance test now in that particular situation, after a couple of hours, you would see ice accretion at the door ceilings of that refrigerator door. In the end, knowing where those leaks are and eventually fixing those leaks is critical not only in the product design and product testing phase in order to evaluate the eventual cooling performance of the equipment, but it's also critical during final testing of the product, because those products will be eventually shipped into the field, into supermarkets, for instance. They will be set up, they will be running for many, many years. And if there were leaks over time, humid air would be sucked into the refrigerator, would essentially be deposed on the fan blades, and would eventually cause reliability issues further down the roads. So this is why it's critical to prove not only during the product design and product verification phase or testing phase that a product is airtight, but also, of course, when it's final tested, end of line, and when it's also brought to the field and to the end customer. So that was a brief rundown of potential applications of our technology in product engineering, product testing in different contexts. In a different context, it may be troubleshooting, it may be trying to meet regulatory requirements, but it may also be a type of quality control that you may want to implement for your products before you submit those to further testing. So in the end, the acoustic camera will help you to identify root causes unambiguously. You may have noticed that before I mentioned that most of the engineers already had an initial hypothesis, which did not prove right in many situations. With acoustic cameras and colorful images, you can effectively communicate your solutions. Everything is pretty transparent what you're doing. You can document also the effectiveness of your measures because you can, as you saw with the construction equipment example, for instance, you can easily locate initially what the sound pressure level of a dominant source was and how that contribution evolved over time as you implemented different measures and solutions. And all of this, of course, helps you to step up your productivity game, meaning not wasting time with trial and error, getting to solutions quickly and effectively implement solutions that really work in the end and bring down your sound pressure levels and let you release your products and start producing your products on schedule and on time. So I would like to thank you very much for your attention so far, and I'm very much looking forward to your questions now.
Thank you so much, Thomas, for your very interesting presentation. We want to open the floor now for questions. Feel free to type your questions in the chat or under the button of the F&A button, and I'll address them one by one. As always, your questions are highly valued, so please share them with us. Here comes the first question around the device itself. Thomas, what exactly is meant by spatial resolution, and in what way does it make a difference in working with your device?
Okay. Very good question. So maybe let's go back to these acoustic images that you see here. Spatial resolution essentially means how big the sound sources appear in your acoustic or optical image. As we saw before, this measurement has been taken with a sensor that has a diameter of 1.3 meters. So this is a pretty large measurement surface for an acoustic camera. If we did that measurement with a much smaller sensor, which may not be well qualified for that frequency range where those sound emissions are happening. With construction equipment, we're typically talking about the most dominant sound emissions happening below 1 kilohertz, maybe up to 2 kilohertz. So if we did that measurement with a smaller acoustic camera, with a smaller measurement surfaces, those heat maps that you see or the sources that you see and the distribution of those sources would be much more spread out. And they, for instance, this source here would eventually stretch up to the top of the cabin, and all of the sources start to blend and overlay. And in the end, you will have the impression, okay, great, I found my construction equipment, but you don't get the required spatial resolution, meaning resolution in space, in order to uniquely identify where certain components are emitting sound. The danger is always when you choose an acoustic camera which is too small, that you cannot resolve and find all of the sources, and you just get a compound blurred acoustic image which does not give you a lot of insights in terms of what your dominant sound emission now really is. So especially when you're dealing with products having mostly low frequency sound emissions, mostly happening below 4 kilohertz, 3 to 4 kilohertz, you should always go for the largest available measurement surface in order to really get to results that point you in the right direction and really that make your analysis more comfortable and more to the point.
Okay, thank you. What type and class of microphones are used in your device?
In our device or in most acoustic cameras, so-called digital MEMS microphones are used. These are highly compact microphones which have a very good signal-to-noise ratio and eigennoise level. They are all coming out of a semiconductor process, so they have very tight tolerances in terms of sensitivity. Which is very important for an acoustic camera application, because in the end, what you want to have is you want to acquire the sound field with microphones that perform equally and which are identical when compared to each other in terms of sensitivity and phase angle at different frequencies. An acoustic camera per se is not cannot be considered like a sound pressure level meter, which has a class 1 or class 2 accuracy. But what we can say, and this at least holds for our equipment and for our technology, that it is comparable to class 2 measurements. What we typically recommend is that you have, of course, a dedicated sound pressure level meter in order to perform your regulatory measurements with a calibrated device, and that the acoustic camera is an additional measurement instrument that you use for troubleshooting, for trying to find out what the root cause is, and for effectively validating your technical solutions.
Okay, and this brings us directly to the next question. Is there any need for calibration? And if so, how often needs the SoundScanner calibration service?
Yeah. So the SoundScanner itself is maintenance free. There is a calibration speaker included, but that speaker is mostly used for aligning the optical and the acoustic image. So it's essentially a single source that is being measured and located. And the nice thing with acoustic cameras is that you can easily identify not only by our software, which essentially does that identification automatically, but you can also prove yourself whether all of the microphones are working by checking the so-called available dynamic range, which is at least 13 dB for our acoustic camera technology. So a calibration, to make a long story short, calibration speaker is included. It's used for aligning the optical image with the acoustic image, and at the same time, it helps you with checking that all of the microphones are working at the correct sensitivity level. Overall, the equipment is maintenance free.
Okay, thank you. And another question around the device. How heavy is the device in total, and can I transport it via airplane?
So maybe let me just quickly step back to the overview of our different sensor variants. The handheld variants, they typically weigh in the order of 1 kilogram only. So this is currently the lightest, the most lightweight acoustic camera in the market for handheld use in the audible frequency range. The P132, which I have to say is the most common sensor being used in product engineering due to the low frequency nature of most of the products being measured, weighs 6 kilograms in total. So this is also the most lightweight acoustic camera in the market, having that size of measurement surface. You can easily grab the acoustic camera by the handlebar and easily carry it around and reposition it. We also have a lot of acoustic consultants using the camera in the field, carrying it around from one room to another, from one floor to another. So portability with that equipment is not an issue at all.
Okay. Looks as if there are no more open questions. Just give it a couple of seconds. Otherwise, I'd say thank you all for your time and very engaging questions. The slides and recording of today's webinar will be available shortly via the link we'll send out. We very much appreciate your participation and look forward to seeing you at our next session. Have a great day.